So as we look for a generator, we're either going to find there is one, or as we work, we may discover a couple elements that generate something of the same size. Now, suppose we didn't know that and we just decided I'm not going to try any of these. Well, that only leaves a few other options. We could try, say, 1, 1. So 1, 1. What happens when we get 1, 1 combined with 1, 1? 0, 2. Then 1, 3. 0, 4. 1, 5. And then 0, 0. So let's see, looking at this, if we've already decided, well, another thing we've realized, hopefully, once we generate a subgroup, none of these elements are going to generate the entire group. They are all going to generate subgroups of this one. This would generate the same subgroup. It's in the 5th position. That's relatively prime with 6. These two would generate a subgroup with 3 elements because they're in the 2nd and 4th position. This would generate a subgroup with 2 elements. So there's another subgroup with 2 elements that we can identify. Going to add with the others. But as we look for generators, if we don't find one on our first attempt, there is no point in trying any of these. They're not going to generate the whole thing either. They will generate a subgroup of what we just generated, and it wasn't the whole thing anyway. So we've got 12 elements here. We are not going to have to try all 12 to find the generator or come to the conclusion it's not cyclic. We pick one. In this case, that eliminated 6 of the possibilities. If we tried another one, and based on what we've kind of looked at so far, maybe 1, 2, because we decided we don't need a 0. A 0 on first or second element is going to mess things up, because that will never move from 0. So we need both elements to not be 0, and 1, 2 didn't appear in this list. So 1, 2, what's 1, 2 combined with 1, 2? 0, 4, and 1, 0, 0, 2, 1, 4, 0, 0. And again, 2 subgroups of the same size, 2 cyclic subgroups of the same size that are not the same. Tells us the group can't be cyclic. Because if the group was cyclic, there'd be only one subgroup cyclic, well, one subgroup of size 6. And we could figure out what it was based on the generator of the entire group. So we don't have to run through all the possibilities on what might generate the whole group if we discover this pattern while we're looking. Are there other cyclic things I wanted to be sure to do? Oh, there is one other thing we've not done a lot of, but is again a bit more abstract, but also, at least it's working with numbers. Now, we've done multiplication in some ZNs. We've always thrown out 0, because 0 doesn't have an inverse. In other ZNs, there may be other elements we have to throw out. But in say Z8, under multiplication, some of the elements have inverses. I mean, what 1 does, right? 1 times 1 is 1. Anybody think of another element that has an inverse?
0.
Under multiplication, 0 times anything will be 0. We can never get back to 1.
Okay.
So in Zn, if we're talking multiplication, we always throw out 0. I mean, if we're talking the group Zn under multiplication, we have thrown out 0 because it will not have inverses. I think we've identified earlier that for 0 to be the only thing we throw out, n's got to be prime. 8 is not prime. But there are some elements in Zn that do have inverses. Three does. 3 times 3 is 1. Can we think of another one?
5.
Okay. 5 times what?
Itself.
5 times itself. There's one more. 7. 7 times itself. So it turns out, really in any Zn under multiplication, the elements that are relatively prime will have inverses. If it shares a multiple with n, it's not going to have an inverse, because there'll be a way that we could get that times something else and end up with 0. And so it turns out if we ever end up with 0 from the product, it doesn't have an inverse. But if it's relatively prime, there will be inverses. Okay. Do we think this group is cyclic?
What does cyclic mean again?
Is there one element that will generate all of those?
At least one? Or only?
Well, in the case of 4, if there is one, there'll be another one. Because if there's one that generates all 4, what's in the third position will also generate all 4. So if we can find one generator, we know all the other generators. And I don't think there's any group, well, I guess a group with 2 elements that's cyclic only has the one generator. But any other group, if it is cyclic, alpha, alpha squared, alpha cubed, up to alpha n, any position that's relatively prime with n will also generate. And unless n is 2, there will be another position that's relatively prime. Okay, so we're not quite sure. Well, let's just start trying. So what does 3 generate? 3, and then 3 times 3 is 1. All right, so 3 didn't generate the whole thing. What about 5? 5 times 5 is 25, otherwise known as 1. Do I need to try 7? Yeah, I mean we could, but at this point, we now have what we said over here. 2 different cyclic subgroups of the same size. The original group is not cyclic. Yes?
So it says just 2. Is it 2 or 2 or more? If like 3 were the same.
I guess it would be 2 or more, but normally as we're looking, once we find 2, we stop. We know it's not cyclic.
Okay.
We don't try to see how many there are at that point. We just know it's not cyclic at that point. Of course, I say that, and I guess, I mean, even if we know it's not cyclic, we could still be asked to find all the cyclic subgroups. So there might be a time, even after we know the answer, that the whole thing's not cyclic, we still might want to decide, well, are there any other subgroups that are cyclic? Normally, if a group is not cyclic, it's going to have subgroups other than just the cyclic ones. Those are a lot harder to figure out what they are. If it's not cyclic. If it is cyclic, all the subgroups are very well defined. Yes?
Now you said that a cyclic group generates all the elements.
Mm-hmm.
Then why are these, what's a cyclic subgroup then? Because it doesn't generate all the elements.
Well, the cyclic subgroup, 3 generates those 2 elements. That is a
That's
cyclic
why it's-
subgroup. The subgroup has been generated by 1 element. The entire group was not. So if we start with an element, it will generate a cyclic subgroup. The question is there any element that generates everything in the group? If there is, then the group itself is cyclic. If it's not, then we just have identified a number of cyclic subgroups, and in this case identified, well, the entire group's not cyclic. It has all these subgroups around that are, but the entire group is not a cyclic subgroup or cyclic group itself. Let's see if this will give us another problem. So let's try Z9. So we'll go to Z9. Under multiplication, the elements that have a multiplicative inverse. So we've got to think, okay, what elements do have a multiplicative inverse? Or maybe what elements don't? In this case, the elements that don't might be easier to identify. What elements share a factor with 9? 3. Is there another one? 6. And 0 is always thrown out. 0 never has an inverse. So the others should. 1, 2, 4, 5, 7, and 8. As we start looking, let's see, 2 times 5 is 10. 4 times 7 is 28. And 8 times 8 is 64. In fact, I think I mentioned before that in any Zn, the n minus 1 is always its own inverse. Because if we take in any Zn, n minus 1 times n minus 1, remove the multiples of n, we're left with the remainder of 1. So in any Zn under multiplication, n minus 1 has an inverse itself.
Wouldn't 1 not work? If this is under the multiplication, wouldn't 1 not be a solution?
I'm not have an inverse? I mean, 1 times 1 is
Okay, never
1.
mind.
Okay. Yeah, I mean, under multiplication, 1 always does. The identity 1 times 1 is 1. And the 0 never does. So our sort of question is then to separate the rest of the elements into those that don't have inverses and those that do. So this is our group this time. We're looking for a generator. I would claim at this point we now know 2 elements that we can immediately exclude from consideration. What's an element we can immediately exclude from consideration here? 1. We can always exclude 1. In this case, there's another one. 8. We already decided 8's its own inverse. 8 times 8 is going to be 1. It's not going to generate the whole thing. So, let's try one of the others. So how about 2? 2 times 2 is 4 times 2 is 8. What, 16? And actually at this point we should get the whole thing.
Yeah.
Because even if the whole group isn't cyclic, every cyclic subgroup should still divide the size of the group, the size of that subgroup. And since this is of size 6, once I hit 4, I'm going to have to get them all. But we can finish this up. 2 times 7 is 14, and 2 times 5 is 10, otherwise known as 1. So we found one generator. What's another generator? Where should we look in our powers of 2? Will 4 generate? Oh, the 4th position?
4th and the 5th,
Okay. Well, one thing we've got to kind of think of here. The size of the group is 6 elements. So as we start thinking of the position, it's the position relatively prime to the number of elements we have in our group. So we're leading relatively prime to 6. 4 is not relatively prime with 6. 5 is. So the 5th position would be another generator. If we want to generate a subgroup with 2 elements, we would look in the 3rd position. The size times the greatest common divisor of position and 6 has to be 6. And so what generates that is 8, which we already recognized was going to generate a subgroup with 2 elements, but that's the only subgroup with 2 elements. And then the subgroup with 3 elements, the greatest common divisor of the position in 6 has to be 2. What positions are that? Where is the position having a greatest common divisor of 2?
2 and 4.
The 2nd and the 4th position. And so the elements 4 and 7 generate a subgroup with 3 elements. Now, certainly with a group this small, we could just brute force it and try all the elements and we'll get the same result. But you really wouldn't want to do that if you had, say, a subgroup with 36 elements. You wouldn't want to brute force and let's see what everyone generates. We can do it if we can find one generator that tells us about all the subgroups. So we decided on this one 2 is a generator. We also decided 5 was. So I'm going to put in here 5 as the generator just to kind of see what it generates. And notice, even when we start with 5, what number's in the second and fourth position? The same 2 numbers that were in the second and fourth position here. As a list, not it's what was in the second position here is in the fourth position and vice versa, but it's the same 2 numbers. In the third position is the same number. In the sixth position, well, always going to be the identity if it's of size 6. So to generate a subgroup of size 2, the number here is 8. Oh. Okay, maybe I've got a mistake. Well, I obviously have a mistake here because 8 should generate it. I wonder what. All right, well, it has a problem with the subgroup. We can at least get the generator. I don't know. It's been at least 2 years since I looked at this. I don't know if I can figure out. So my hopefully now working. One thing I've discovered as I put these together with GeoGebra, GeoGebra is public domain and people are working on it. So occasionally in some of their upgrades, something that I had working later isn't working anymore because somebody made some change in the code to fix some other problem and messes up something in what I had done or what I thought I had working. Because at one point I definitely thought I had it working, but that's not the case. Okay. Let's do one more. So this time we'll do the elements in Z12 under multiplication that have an inverse. So we first have to decide, okay, well, what are those numbers? Let's see. Do we expect 2 to have an inverse?
5.
All right, 5 would.
Sorry, I skipped mine.
Yeah, you jumped right over 2, 3, 4. Why'd you jump over 2, 3, and 4?
Because 5 was the easiest to find.
Oh, so you were actually thinking invert. I mean, 2, 3, and 4 share a divisor. 5 does not. 6 does, so it's not going to be in the list. 7 does not. 8, 9, 10, 11 does not. Well, let's pick an element. You said 5 was easy to find, so 5 times 5 is 25, otherwise known as 1. So 5 is its own inverse. 11 squared is 121. Well, that's also then 1. And again, n minus 1 squared is always going to be 1. Do I really need to try 7? I'm hearing some confident no's. 2 subgroups, two different cyclic subgroups of the same size. The entire group is not cyclic. 7, in fact, here is also its own inverse. And interestingly enough with this, I mean, I've been kind of saying this, but if we were to fill in this whole table of multiplication, let's see, 5 times 5 was 1, 7 times 7 is 1, 11 times 11 was 1. What's 5 times 7? 35, otherwise known as 11. 5 times 5 is 55, otherwise known as 7. We're not getting any new elements in this. 7 times 5 is 11. What's 7 times 11? 77. Yeah. 72 is a multiple of 12, and then it's 5 left over. And so we've got 7 and 5. So we do end up, if we fill the complete table out, with the things we've discovered with other tables. We don't get any new elements. None of the elements are repeated. That's something we've discovered earlier in terms of a group. In any row or column, none of the elements can repeat. We've got to get the identity somewhere so that we have inverses. No new elements, because then the operation isn't closed. And that's why we've thrown out, say, 2, because 2 times 6 is 0. We'd end up with a new element. So we don't have an operation, and 0 is thrown out because it doesn't have an inverse. So there are some sets that we can build still using a familiar operation, but it's a bit more abstract. We can talk then about, is that group cyclic, and do some work in that group. Trying to think, we'd actually done another we've encountered another one that had 4 elements. One was its own inverse, right? Was that the Z8 under multiplication? One was 1, 3, 5, and 7. Three times 3 was 1, 5 times 5 was 1, 7 times 7 was 1, 3 times 5 is 7, 3 times 7 was 5, 5 times 7 is 35, otherwise known as 3. Certainly with something like this, it's a lot harder to spot. These two groups are isomorphic. They both have 4 elements. Every element's its own inverse. It would be a lot harder to come up with a mapping on how we map from one to the other, and that the mapping really preserves the operation to build that isomorphism. The isomorphisms we're going to see or the mappings we're going to see as potential isomorphisms are going to be things we can describe nicely. Send x to 2x or x to negative x. So it's something we can describe more mathematically. This one I think we just have to just say, well, I'm going to send 1 to 1, I don't know, 5 to 3, 7 to 5, 11 to 7. And this is even more complicated in that some of the numbers appear in both sets, both groups. So it'd be a lot harder to even get our hands wrapped around this to figure out, well, what is an appropriate mapping here. But the whole idea of isomorphisms of groups, the sort of underlying motivation of that is, as we study groups and different groups, sometimes we happen on 2 groups that are the same size and seem to have pretty identical features, does it really matter what we call the elements? You know, or could we just call the elements something totally random? You know, E, A, B, C. E being the identity, and then the rest we could just kind of rename A times A as E, B times, and C times, let's see, I guess, CB, CB, and that leaves that being A. And A meets all the criteria, far more abstract than something we can identify, but it's just renaming the elements but keeping the structure. And so if we do have isomorphic groups, perhaps there's a structure that makes the most sense to us. Well, that would be a good structure to work with then. If we've got one of the isomorphic structures, let's use the one that seems to be the easiest for us to understand. I mean, in general, that's one of the big things we try to do in mathematics is keep working with a problem until we get a form that's, oh, I know what the answer is. We want an equivalent form, an equivalent form, an equivalent form, until, oh, I know the answer in solving an equation or a system of equations. There are things we're allowed to do that don't change the solution, they just change the form. We do it again, until we can see what the answer is. We certainly don't want to do anything that changes the form, or changes the answer, because how's that going to help us solve the original problem? But a different form might be easier to work with. And so that's kind of what happens in terms of isomorphic groups. If we can decide two groups are isomorphic, I mean, for me, either one of these two is easier to think about than this one. I mean, this one, I pretty much have to see the table to duplicate these operations. And this one is very abstract. It's like, where did any of that come from? At least in these two, we've got a sense of where the operation came from. Other questions? Okay. If you've got the homework now and want to turn it in, that's fine. Tomorrow, did I say a specific time tomorrow? I did not. I just said tomorrow. But by 5, I think I can get them graded tomorrow night. So if I don't get them by 5, they won't be graded by Wednesday for you to have then in reviewing for the exam. And the exam then is Friday. So I will see you. And if I'm not there, just put it in the box outside my office.
I did some. Yeah. Do some numbers.